proposed back in 2002. He then he was there, but now he has University. So it has basically two concepts from where this term comes, the non-dominated sorting. First term is non-dominated sorting. So we have already discussed what is the non-dominated set. So given a set of solutions, we can find a non-dominated set.
Here we are considering two objective functions. For approach we are taking three variables. For objective function, we may not different variables, maybe more than 3 or 2.
Overall, there is a number of variables in the decision space. You have to choose one. It may happen that some objective function is using a subset of those variables.
That's what I mean.
It can be.
The same variables are fixed, so they won't be 10.
Yeah.
It may depend.
Some objective function is using 5 variables.
Or that's a part of the other function.
So in non-dominated sorting, what we are doing is that it is basically a mechanism of classifying the set of solutions in a set of solutions in different classes of solutions, in different layers of solutions, such that so this is a mechanism of ranking the solutions. I will discuss with an example that will be better. And another is, so as we have discussed the two goals of multi-objective optimization, one is to progress towards the Pareto front. That is actually taken care of by this non-dominated sorting. And another goal is that to find all solutions, the complete span of the Pareto front. So that's why it is necessary to have diversified set of solutions in a population. So that is taken care of for diversity maintenance. There is a concept called crowding distance I discussed. This is used for maintaining the diversity in the population. And also we can have elitism here. That is a mechanism of elitism. Elitism means that to keep track of the best solutions from super. And in general, we can use it, the time complexity of it is that for a particular generation, that doing all these things is order of n squared, that m is the number of objectives and n is the population size.
Can you repeat this point?
Yeah, I will give the example that. So non-dominated sorting. So suppose we have two objective functions, f1 and f2, both are of many-function type. So in a certain population of solutions, we can plot this solution. We have plotted these solutions in this objective space. So we have several solutions in the population, and these are the plotted. We have plotted these solutions in this space. So I am showing it for the two objectives, but you should generalize it for many objectives, all possible objectives. So non-dominated sorting means that classify these solutions in different layers, different ranks. How? So first what we do, so both are minimization objective functions. What is the non-dominated set in this solution set? We find that. What is the non-dominated set of solutions in this set? What is the non-dominated set of solutions? So these are the non-dominated set of solutions in this solution. We can write that algorithm that we have already discussed. This thing we have to write the algorithm for that. By that we can find the non-dominated set of solutions from a given set. We call these solutions as the rank 1 solutions. Rank 1 solutions, obviously, because among all the solutions, these are the better ones, because these are not dominated by any other solution in the set.
Sir, are we considering only the minimum case?
Just for example, but this should be generalized. Generalized in the sense that it can have, instead of two objective functions, you can have several other objective functions. And instead of both are of same type, minimization, it can have certain objectives are maximization, certain objectives
Like
are
previous.
minimization. That can be
In
done.
the previous.
But generally what we prefer is that to ease the implementation, we convert all the objective functions in one particular form, either minimization or maximization. So suppose if there are two objective functions which are of minimization type and one is maximization type, what we can convert that the maximization objective is converted into minimization. Just by making, suppose, the reciprocal of the objective or just taking the negative of the objective value. So that will be converted into minimization. Then it will be easier to implement all the. So these are the rank 1 solutions. Then what we do? We temporarily ignore these solutions, rank 1 solutions. Just temporarily forget about these solutions, forget that these solutions are there. Just temporarily ignore these solutions. And then run the same non-dominated operation on the rest of the solutions. And find a non-dominated set of solutions from the rest of the solutions. So which will be those solutions? So these are those solutions from the rest of the solution set. These are the non-dominated solutions. So we call them as the rank 2 solutions. All these solutions are rank 2 solutions. So this will be repeated. So again, we just remove these solutions temporarily, both rank 1 and rank 2 solutions. And from the remaining, we again find the non-dominated set. Those will be rank 3 solutions. Then we find the rank 4 solutions, rank 5 solutions. How long it will continue? Until all the solutions are classified into some rank. So in this case, we have total 7 ranks, 7 set of solutions, 7 classes of solutions, right? So this whole process is known to be non-terminated sorting. So from here actually, because why sorting? Because we are sorting the solutions according to their non-domination relationship. So from these, the term non-dominated sorting genetic algorithm comes. Now, one thing is that, so the main issue is the selection, as we have already discussed. So normally in NSCA2, we do a binary tournament selection. Not roulette wheel selection, it is binary tournament selection. And because there are other mechanisms to implement the diversification, like the crowding distance and mutation is there. So usually binary tournament selection method performs more or less equally with the roulette wheel selection. So for ease of implementation, binary tournament selection is better. It is easier to implement. So here binary tournament selection is used, but with some modification. Because what happens in normal binary selection, binary tournament selection? From the set of solutions, we pick up 2 random solutions and put the better one in the mating. So this is your binary tournament. So same thing if we want to do the same thing here. So suppose given this set of solutions, we pick up 2 random solutions. 2 things can happen. These 2 solutions may come from 2 different ranks, 2 different classes. Suppose one solution comes from rank 2, another solution comes from rank 4. So which solution will be preferred and will be put in the mating?
Rank
2.
Obviously rank 2 solution. So there is no problem when these 2 random solutions are coming from 2 different ranks. Problem begins when they are coming from the same rank. Which solution should be chosen? In the previous NSGA to first version, NSGA, that is the first version of NSGA, they used that when the solutions are coming from the same rank, they were choosing a random solution from that group. but NSGA2 has a better approach. Let me discuss that. So,
Sir, what happened in NSGS 1 you said?
NSGA1, what they do is that when the two solutions are coming from two different ranks, fine, the lower rank solution is
same.
put in the middle. If they are coming from the same rank, then between these two, a random solution is put in the middle. But in NSGA2, what they do is like this. They introduce a concept called crowding distance. What is that?
Why you are preferring binary tournament? Is there any?
I am not preferring actually. They have used, this is not my work. I am discussing the most popular work in multi-objective literature. So they use the binary tournament. Probably that is the ease of implementation and ease of modification in terms of multi-objective. That's it. Well, so what is done? So the problem is that when two solutions are picked up, random solutions are coming from the same rank. So same rank means same prompt, same non-dominated prompt. So for this, they apply the crowding distance. What is crowding distance? Suppose this is a non-dominated front, a particular rank. Each of these solutions in that front is given a value, which is called the crowding distance. What is the meaning of crowding distance? I just tell you. First, let me explain how that is given. So the two end solutions. So if you have three objective functions, you will have three end solutions. Right? Two end solution means that here the solution which gives the best value of f1 and the solution that gives the best value of f2. So if you have n number of objective functions, you have n number of best end solutions. So all these end solutions are given a distance value, crowding distance value infinite. Infinite means practically a very large value. When you are going to implement it, just put it a very large value. Now, if we want to find the crowding distance of, suppose, solution I, solution I is crowding distance. It is defined like that. We just consider the solution I minus 1. That is the solution just before I with respect to one objective function. And the solution just after I with respect to the objective function. So solution I minus 1 and I plus 1. Then we virtually create a box around this solution with respect to these two solutions. And the crowding distance value we put for this solution is the area of this box. Similarly, the crowding distance value of this solution will be the area of this box. Now, what does it signify? This area. So, if we say that the crowding distance of a solution is larger, what does that mean? It means the solution is not crowded by many other solutions. It is situating in a less crowded region in the front. So larger crowding distance means it is in a less crowded region. Smaller crowding distance means there are other solutions nearby. Right? So what is the advantage here? Now we modified the binary tournament selection like that. It is called the crowded binary tournament selection. So what we do here? So again, we pick up two random solutions from the set. If the solutions are coming from two different ranks, no problem, put the lower rank solution. You don't need to see the crowding distance, etc. You just put the lower rank solution in the middle. But if the solutions are coming from the same rank, then you find the crowding distance values of these two solutions. Which solution will you prefer? Whose crowding distance is larger or whose crowding distance is smaller? Larger. Why? Because it is situated in an area of that front which is not covered by much solutions. So if we lose that solution, there is a chance that we lose that part of the parallel front. Because our goal, the second goal, is to capture the complete parallel front. Right? So if these two random solutions are coming from the same rank, we take the solutions which has larger coverage distance.
So one question here, by default, when choosing the random value, the two are the boundary value, n value, and both are the.
So always, if we whenever two solutions, one of these solutions is a boundary solution.
Then one is set to infinity.
Yeah, that will be always selected.
That means suppose both are the, that means if for this example two.
You have to choose one of them random, or you may put both of them, because both are infinity means you are sure that these two are boundary solutions. So better you put both of them in the middle, because you don't want to lose the boundary solutions. So because that defines the end of the parallel front, two ends of the parallel front, right? So this is the concept of crowded binary two-dimensional selection. That if you have if the two ranks are different, you choose the lower rank solution. If two ranks are same, then you choose the solution with the larger coverage distance. That's all. This is your NSGA2 because the rest of the things are same. So we start with the population, initial population, then we perform a non-dominated sorting on the set sub-solutions. We give the ranks to the solution, rank 1, rank 2, rank 3, etc. Then we perform crowded binary two-dimensional selection, create the mating pool. Then we perform the crossover and mutation. Then there is an elitism operation. In elitism, how this is performed is like this. What the basic objective of elitism is to not to lose the better solution, the good solutions. So it will be better if we compare the two populations, the parent population and the child population, and consider the better, the combined from the combined population, the better solutions are put in the next equation. So for this purpose, what is done is that they combine the parent population and child population. So if the population size is P, so now it becomes 2P. Then it applies non-dominated sorting on the combined population. The same approach, the non-dominated sorting is performed now on the combined population. So finally again we have to choose P solutions from it, because the population size is kept constant overall. So it has become 2P, but now from 2P we have to choose P solutions. So which P solutions will be chosen? Obviously we start from the lowest rank. So suppose here all the rank 1 solutions are chosen, then rank 2 solutions. But rank 3, if we cannot choose all the solutions from the rank 3, because that will exceed P. So which solutions from rank 3 will be chosen? These solutions will be sorted by their crowding distance values, and we will take those solutions from the top in descending order crowding distance values, and from the top the remaining number of solutions will be chosen to fill up the complete population. P number of solutions. Right? So again from this set of solutions, so this is the elitism purpose, and then just go for selection, then again mating pool is created, crossover mutation, then again combination. So this goes on. So this is the main loop. Generations are running. Which one? Elitism?
So if you won't take that.
Yeah, PI and CI. Then we
Yeah.
both combine.
So what happens is that it combines the two populations, the parent population and the child population. So if the population size is P, now it becomes 2. So So two populations are combined, but in the next generation you can only take P solutions. So from these two P solutions you have to choose the P solutions. So what is done? This combined population is sorted with the non-dominant sorting method. So that means they are ranked in different, the different solutions are ranked in this fashion. Then, so suppose the P equal to 50, there were 50 solutions, but so this size is 100, and suppose this is 25, this is 15, so 40 comes, and these rank 3 solutions, there are 40 rank 3 solutions. But you cannot take all 40. You can take only 10 from that. So which 10 will be selected? They will be sorted in descending order of their crowding distance values, and from top 10 solutions will be selected. So overall again 50 solutions will be sent to the next solution. Right? So this is the generations, and that will be that is basically your NSC. So in the difference with NSGA and NSGA2, that is the first version of NSGA2 and NSGA2, is that in the first version the no concept of crowding distance was there, and there was no elitism also. So just the child population goes through the next version. So in NSGA2 they implemented these two concepts, the crowding distance and the elitism in this version, and it has been proved to be much better result than NSGA. So if you want to apply your NSGA2, there are some multi-objective benchmark multi-objective optimization problems, because whenever if you want to design your own multi-objective algorithm, you have to prove that your algorithm performs better on certain problems which are known as benchmark problems, standard problems. So some benchmark problems are just hello. I'm making best person to lecture. So some of the benchmark problems are like these, that so all these problems are of two objective problems, but the number of variables are defined. So for example, in this problem, two objective functions are x square, another is x minus 2 square. The bound of x is given between 0 and 2. And so this is one variable function, one variable problem. This is again two objective functions, but three variables. Okay? Three variables. This is also a three variable functions, two objective functions. This is two variable objective functions, two objective functions. Some more are like that. This is an 30 variable functions, 30 variable problem, that's ZPT1. So all these are 30 variable problems, so all of them are minimization. I implemented some of them in MATLAB. If you are interested, you can find the NSGA2 code in MATLAB. It is there, and also you can go to the site of Kanpur Genetic Algorithm Lab. That's a very funny name. That's called Bengal. You can search with Bengal, you will get the link. Kanpur Genetic Algorithm Lab. There you can get the code for NSGA2. So I implemented myself in MATLAB some of the problems. So this is the first problem, that is x square x minus 2 square. So this is the Pareto front we got. So FON is another, the second one, that three variable problem. So here the Pareto front is concave type, not convex, right? But you see that these functions are also of minimization type. So it is not necessary that always the minimization objective means the font will be like this. It is not tensor. It can be any font. It can be like this. So it depends on what? It depends on the search space, shape of the search space. So in other words, AUR, so this problem you can have the discontinuous kind of character font. This is also discontinuous. So maybe why it is discontinuous? Maybe I don't know that. Maybe the search space is like this, that here and then here like that. So this part is removed from the character font. So only this part is there. So this is another one. This is again a front page type of font. This is also nice. So this is also search space is like this actually. So that's why only these parts. So these are the benchmark problems. So if you want to design your own algorithm, you have to prove that your algorithm performs good on these problems. You cannot give your own problems and show that my algorithm is performing good for my problems. Nobody will. So, are you interested anymore in some applications or?
Please, sir, if you can.
So we applied in many applications. We have applied multi-objective genetic algorithms in many areas. One of them is this in bioinformatics. Now there is a. I have to discuss a little bit of biology. So what happens in our body? So we know that our body is made up of several cells, millions of cells. Now within each cell there is a nucleus, and within the nucleus we have several chromosomes. So how many chromosomes are there? 46. So 23 pairs of chromosomes.
Yeah.
23 pairs. We are not saying 46. We are saying 23 pairs. Because each pair in a particular person, each pair is coming one from its
Father and mother.
One from father, one from mother. Okay. So out of these 23 pairs, 22 pairs are known as autosomes, and there are 2 sex chromosomes. We say that X and Y. So if you are female, so your sex chromosome both are X. If you are male, then you are X and Y. You know that. So in a chromosome is usually made of DNA, a particular acid, which is called deoxyribonucleic acid. A DNA is nothing but it codes the information. So what our cells will perform, what will be the functions of our cell, all these information are coded in a DNA, but not all the parts of the DNA. Actually, the length of the DNA is, so DNA, as we discussed in the previous session, that DNA is basically composed of a number of nucleotide bases, 4 nucleotide bases to be specific, adenine, thymine, guanine and cytosine, ATGC. So DNA is a string of these ATGCs. Usually it is a double helix, double stranded. So anyway, I am not going into very details of that, but what I want to mean is that in a DNA, not all the parts of the DNA has information for the cells, but only some parts of the DNA. So usually a DNA is, in human bodies the DNA is very long. It consists of 3 billion bases. Bases means one base is adenine, another base is thymine, like that. So a DNA strand composed of 3 billion bases. The complete genome of our body consists of 3 billion bases. So what I want to mean that not in all these length, complete length, the DNA contains information, valuable information. Rather, only the parts, some parts of this DNA contains these information, and those parts are known as genes. Okay, so this is my DNA, basically a strand of ATGs, and only some parts of this DNA. So this is another one part, this is one part, this is a small part like that. So these are the genes, where all the information, necessary information, how our cells will perform, how our cells will